Hello and welcome to this video on phase and frequency noise. In this video, we're going to investigate how the spectrum of the electric field, as well as the spectrum of the phase and the spectrum of the frequency of a laser, are impacted by the presence of phase noise. First of all, let's begin by defining what we mean by phase noise. Here we see an expression for an ideal, complex electric field that oscillates with a carrier angular frequency of omega naught. And I've also plotted the real part of this field over time, and you can see that it simply becomes a wave that repeats at consistent intervals. A more realistic expression for the electric field emitted, for example by a laser, would be something like this, where apart from the carrier term, we also have a phase term like so that could potentially change over time. And the main impact of this phase term is to change the location at which the recurrence of the wave happens. So you can see for the first cycle here, the wave actually repeats a little bit earlier than we would have expected from an ideal field, and this implies a positive phase shift. Then if we slide over the next part of the wave, we can see that it repeats a little bit later than expected, implying a decrease in the phase. And if we repeat this for all the different cycles of the wave, we can gradually build up a graph of the phase function over time. Of course, in this case, I'm doing this in sort of a semi-discrete manner by only considering the exact location at which the wave crosses zero, but in principle you can compare any part of this ideal wave to the corresponding realistic wave and then figure out the phase function in a completely continuous manner. I also want to stress that the phase function in principle can be any arbitrary function of time. For example, for a very idealized laser with no phase noise but some deliberate modulation, you can see that if you, for example, modulating it with a commercial phase modulator, it might have a term that's very large in amplitude and oscillates very quickly. But if that experiment is being carried out in a laboratory where an air conditioner is gradually cycling on and off over the course of a day, there might also be a very slowly varying term, like so. And of course, any kind of phase variation that you might be interested in can be built up from a sum of a large number of cosine terms or sine terms. This is basically just the idea behind Fourier analysis, which we're going to be using a lot in the following slides. So the question arises, since this phase function is present, what's the best way to explain or to highlight the impact of this phase noise on the properties of the laser? Before we get into the exact details of this, I want to explain that the typical model that we use for the phase evolution of a laser is going to be a random walk, which I've generated numerically here in gray. And both this graph and all the other ones we're going to be showing in this video are generated using a Python notebook that I've linked to in the description that you can of course download and play around with yourself. So anyway, this random walk is very frequently a good model for the phase evolution for reasons I explained in a previous video linked right up here. And I've also generated this same random walk here, but with a 30 gigahertz phase modulation sitting on top. And you might be able to see that this yellow trace here sort of follows the overall pattern of the gray one, but has this more high frequency variation sitting on top of it. And this is just to compare the impact of the sort of baseline behavior of the phase noise of a laser to one where we're doing a very simple modification to it of just modulating it at a single frequency. So anyway, first of all, we can look at the spectrum of the electric field by factoring out the very fast but also very predictable oscillations happening at the carrier frequency to obtain this expression that is just the envelope of the electric field. If we compute its Fourier transform and then its absolute square, we essentially get the power spectrum of the electric field of the laser. And if we graph this out as a function of frequency, we get the following two traces like so, where the gray one is still for the pure random walk and the yellow one is the same random walk but plus this 30 gigahertz modulation sitting on top. And by itself, this plot is not very informative because it's kind of noisy and a bit chaotic. But it turns out that both experimentally and theoretically, actually I did an experiment with this that should be linked right up here, you can show that if the underlying phase walk is just a random walk, then the average spectrum is going to look like a Lorentzian in the frequency domain like so. And essentially this Lorentzian will have a line width or a full width or maximum that is proportional to the random walk step size squared divided by the magnitude of the time step. So this kind of plot of the electric field spectrum is very useful if the thing you care about for your particular application is how much power leaks from the central frequency of the laser into other frequencies. For example, if you're doing some kind of experiment where you don't want too much interference between two signals, then you're really interested in the way that the phase noise causes this laser line to broaden, and you don't want the broadening to be too large, presumably. But kind of a limitation of this kind of plot is that oftentimes when you look at let's say spec sheets for lasers that you might want to buy for your laboratory, they'll state the line width in, for example, megahertz or kilohertz or whatever. and use that as a metric for the amount of phase noise, because obviously if there's more phase noise, this line is going to be broader. But that's only really applicable if the underlying phase walk is actually a random walk. So again, presumably when they state that in spec sheets, they've tested that the phase function is a random walk. That's why they just state the line width. But in principle, you could also be measuring a laser in your given application where the electric field spectrum looks more like the yellow curve here. And okay, you could sort of look at the full width or maximum of the yellow trace here, but clearly it doesn't look like a Lorentzian, it looks like something else. And we can sort of see that the yellow curve has like a cut or like a kink happening here at 30 gigahertz. But again, it's not really obvious from the shape of the yellow trace what exactly is going on. Like if you have the gray trace here that's Lorentzian, that's very good because you know it's a random walk. But if you were to measure the yellow one, you wouldn't really be completely sure about what underlying phase evolution is happening. So the point I'm trying to make is that the electric field spectrum is very useful if the thing you care about is how much power gets transferred from the carrier frequency into adjacent ones. But it doesn't tell you very much about the actual exact behavior of phi of t. So for that reason, we're going to now analyze phi of t directly and its Fourier transform. In order to do this, the first step we can take, assuming that we've measured phi of t over time somehow, is to subtract the average value away from this trace, because it gives us a new trace where the height of it just tells us the phase deviation away from the average at a given instant. For example, maybe it's 0.75 radians in this particular case. So that's sort of a good start, but still a bit uninformative, because essentially this graph here is just a graph of the sort of historical record of how much the laser's phase deviated away from the average at a certain instant in the past. But what we really like is some kind of metric that tells us how much we can expect the laser to deviate away from the average in the future. So to generate this, we can simply compute the RMS variation in the phase, or phi RMS. Essentially, we just take this whole graph here and compute it square, and then take the average of that squared value throughout the duration of the measurement, and then finally take the square root. And if you've done a bit of signal processing, this should be fairly familiar to you. So this gives us a metric for the typical deviation away from the average phase that we can expect. And in some sense, you can actually think about phi RMS divided by omega naught as sort of the typical timing error of the laser compared to an ideal laser operating at the same frequency. And sort of think back to the first explanation I gave of the definition of phase noise. This should make sense. So one thing to be aware of is that if phi RMS is a random walk, then its value will actually be proportional to the square root of the measurement duration. And to illustrate this, I've generated a random walk here that has a phi RMS value of 8.8 and a duration of 2 nanoseconds in total. But if I quadruple the duration of this walk, we can see that it roughly doubles the value of phi RMS in correspondence with this behavior here for random walks. So just be aware that if someone states the phi RMS of a given laser in the phase domain, it's dependent on the measurement duration of that phi RMS value. Now, another thing about phi RMS is that it's very useful for telling you sort of the expected deviation away from the average, but it doesn't really tell you how that deviation actually happens. Because here we see a random walk marked in gray that has a phi RMS value of 12.3, but we also see another trace marked in blue, which has a phi RMS that's almost the same at 12.5, which seems way more chaotic and much less predictable than the random walk. So it's possible for two different phase evolutions to have the same phi RMS value, but for that variation to actually happen in two very different ways. So to get a better picture of how the deviation actually happens, you probably already guessed that we need some Fourier transforms. But before we get into that, I want to just make a quick side note about two-sided and one-sided spectra. Essentially, if you have a real signal, which this phase function will always be, and you compute its Fourier transform, then the spectrum is going to be Hermitian. And essentially, this just means that whatever spectral value you get for a positive frequency, you'll get exactly the same one for a negative frequency over here, apart from a complex conjugation. But as soon as you compute the absolute square of this spectrum, the conjugation just disappears, and you get the same thing for the negative frequency as for the positive frequency. So in some sense, there's really no point in reporting the negative parts of the frequency. You might as well just report the positive part twice, in other words, by scaling it by 2. So just be aware of this if you're reading papers on phase noise and frequency noise and whatnot, even relative intensity noise. If you see a one-sided spectrum, they've basically taken the real signal, computed the Fourier transform, taken the absolute square, but then only shown the positive part scaled by a factor of 2. So just remember this factor of 2 if your numbers aren't adding up. Anyway, let's take a look at the Fourier transform of a typical random walk. So I've generated a random walk right here with a phi RMS value computed, as I showed before, of 12.29. And then let's take the Fourier transform and compute the absolute square. What we get is something that looks a bit like this, and you probably already noticed that this has an interesting linear behavior, at least when you plot it on a double log scale, And we're going to return to this linear behavior in just a moment. But first of all, note that we can also compute phi RMS in the frequency domain and get the exact same value. And the reason for this is simply Plancheral's theorem, which essentially just is a nice property of Fourier transforms that they conserve the integral of the absolute square of whatever they're applied to. And if you've done a bit of quantum mechanics, you're probably already familiar with this fact. So what else can we say about this? Well, we can notice that the units of this spectrum are in radians squared per hertz. And the underlying message here is that the spectrum is basically telling us how much of phi RMS squared is due to changes happening on a particular time scale. For example, the fact that the spectrum has a very large value here for a low frequency means that much of the variation in the underlying random walk is happening on a very slow time scale, and correspondingly little of the total variation happens on a fast time scale. And going back to the previous random walk here, we can actually see that in action, because clearly the random walk is oscillating at a fast frequency, but those fast frequencies have a fairly small amplitude overall. However, if we take a look at what happens from this time here to this much later time on a very slow time scale, it takes the random walk all the way from plus 20 down to negative 20 down here. So in other words, this kind of explains why the spectrum is very high for a low frequency, because much of the variations happen on a low frequency, and why it's so small for high frequencies, because all of the very small contributions don't really have a high amplitude. Another thing that the spectrum is useful for is determining the phi RMS value for a situation where you have a shorter measurement time and maybe a lower maximum frequency. You can sort of imagine that maybe you've measured the spectrum using one particular setup, but then you want to measure it again for the same laser using a different setup where you don't measure for a very long duration, and also the equipment isn't as sensitive to high frequencies. So in that case, you can simply draw in the new cutoff frequencies determined by this shorter measurement time and the lower maximum frequency, and then simply integrate the exact same spectrum in this region to obtain a phi RMS value that's going to be shorter than the original one, like so. So again, kind of useful to keep in mind if you want to, let's say, take one laser, measure its spectrum, and then deploy it in another application. What else can we say here? Right, let's take a look at the phase spectrum for the random walk plus the 30 GHz modulation sitting on top. In this case, you very clearly see that there is a very strong component here at 30 GHz. In fact, it's much more clear what's happening here compared to the electric field spectrum, where we saw only these sort of maybe slightly uninformative cuts at 30 GHz. But now we see a very clear spike happening here. So it's very clear that there is this additional modulation sitting on top of the random walk. So in short, the phase noise spectrum is very useful if the thing you care about in your experiment is timing. But it's also less informative if you care about how the optical power causes interference between different channels. So again, very useful if you may be doing something where you're using a laser or some kind of oscillator for a timekeeping experiment, but not so useful if you care about interference. So returning to this linear behavior we see here for the double log plot, if we draw a straight line that sort of trails the spectrum, we can see that if we scale up the variation frequency by a factor of 10, then the strength of the spectrum decreases by a factor of 100. And this implies that at least when the phase function is a random walk, then the spectrum is going to scale as 1 over f squared, like so. And this turns out to actually be a property that's due to the random walk. Essentially, what's interesting about the random walk is that the current phase is the previous phase plus or minus some randomly chosen offset here. So there's some kind of correlation between the past, the present, and the future for the random walk. But if we simply choose the next phase from a Gaussian distribution with no correlation to the past, then in some sense the Gaussian process instantly forgets what just happened to it. And the point here isn't that this is supposed to be a Gaussian process, it could also be a uniform distribution or a triangular distribution or something else. The point is just that when there's no correlation between the past, the present, and the future, you get a very different behavior compared to the random walk, but there is such a correlation. Mathematically, we can actually compute the autocorrelation of both the random walk and the Gaussian process using this expression here. And essentially what this means is just that we take the original trace and then shift it over slightly relative to itself, and then check how self-similar it is. And if we do this for the random walk, we see that it very gradually decreases towards 0. So in other words, the random walk only gradually stops looking like itself as we shift it over in time. But the Gaussian process is basically just a single delta spike here at 0, meaning that it instantly forgets what happened to it. So with that in mind, if we compute the spectrum of the Gaussian process here, we get something that's completely flat. And we can either compute the spectrum by simply taking the Fourier transform of the phase trace and then computing the absolute square, or we can take the Fourier transform of that autocorrelation I showed on the previous slide. And this is basically going to be the same thing thanks to something called the Wiener-Kindchen theorem. And you can look that up if you want to. So anyway, the point is that when we see this sort of flat spectrum in the phase domain, it means that we have sort of memoryless behavior, whereas 1 over f squared behavior implies that a random walk that's correlated is the thing that's causing this particular phase variation. So I mentioned this because it's very useful to keep in mind when analyzing other spectra as well, because a lot of different processes in nature and biology and even finance actually are well described by both either a memoryless process or a random walk or some combination of the two. So when you're looking at spectra of different things, if you see this 1 over f squared behavior, you can reasonably assume that a random walk is underlying it. But if you see something that's completely flat, you can imagine it's probably some kind of uncorrelated noisy process going on. Okay, so and just for good measure, I've also gone to the internet and found some spectra for different lasers that we can analyze. So here we see two different lasers and their phase noises being compared. Note, by the way, that in this case, they're actually plotting the absolute value of the spectrum rather than the absolute square as I've done before, but the underlying logic is still the same. For example, for the red laser, we can see that it's undergoing a random walk here, because if you scale up the variation frequency by a factor of 10, then the strength of the spectrum decreases by roughly a factor of 10. And again, it's a factor of 10 instead of a factor of 100, because they're just plotting the absolute value of the spectrum. Furthermore, we can see that there's probably some environmental disturbances causing these variations that happen on a very slow time scale between 10 seconds and 1 second. However, for the blue laser, we can see that it's mainly exhibiting white noise behavior in the range from 1 Hz up to 10 kHz. And somehow the environmental factors that impacted the red laser have been compensated because its spectrum is much, much lower in the same region. So I've linked some more notes about this kind of 1 over f noise behavior in the video description, so you can check out if you want some more information. Okay, so with all of this out of the way, we can apply some of the same logic to frequency noise. Because if we have this phase noise trace as we generated earlier, we can actually just compute the instantaneous frequency of the laser by taking the derivative of the entire phase expression here. So we get just the carrier minus the derivative of the phase over time. And if we just look at the instantaneous frequency, or rather the instantaneous frequency shift away from the carrier, we get this expression here where we divide by 2 pi to convert the phase from radians to cycles, and therefore hertz. And now we can simply do the exact same thing as we did before for the phase noise. So if we have a frequency noise traced like so, and again note in this case it's going to look a little bit weird and spiky and blocky because it's generated based on a random walk where the step size is always like plus minus 1. So we get this sort of weird, very discrete behavior. But apart from this, the exact same logic applies, of course. We can just subtract the average value of the frequency, which in this case is just going to be 0, and then compute the RMS value of the frequency deviation as we did before. And in some sense, it's actually very useful to think about this FRMS parameter here as sort of the typical deviation in the color of the laser, because of course the color of a laser is determined by the carrier frequency it has. So this is sort of the deviation away from the average color, the average carrier. Now we can also compute a spectrum of the frequency noise by just computing the Fourier transform of that frequency function in the time domain. And here we see a typical frequency noise spectrum when there was a random walk in the phase domain. Note that it's completely flat for most frequencies, and this sort of dip that happens here, I think is just a numerical artifact of the way I've generated, so don't worry too much about that. The intended behavior is just for it to be completely flat for all frequencies. Of course, we can also compute the FRMS value from before by simply using Planck-Dual's theorem and integrating the spectrum here in the frequency domain. And the point from earlier about selecting a shorter measurement time and a lower sensitive frequency, that also still applies. Note also that the units of these frequency noise spectra will be in hertz squared per hertz, which at first glance seems like a very strange unit to use. But again, it's just telling us the contribution to the total variation in the laser color compared to the frequency at which that variation is happening. So for example, in this case, we can see that whatever frequency variation this laser has, there's sort of an equal contribution from very slow variations and very fast variations happening up here. Okay, another kind of interesting fact here is that when computing this frequency noise spectrum, there's basically two ways we can go about it. On the left-hand side, we simply take the Fourier transform of the instantaneous frequency and then compute the absolute square afterwards. But it turns out they can actually get the frequency spectrum from the phase noise spectrum directly. Essentially, this comes from the fact that the Fourier transform applied to a derivative is the same as I 2 pi times the frequency multiplied onto that Fourier transform applied to the intended function. So you can see that if things cancel out here and we compute the absolute square, we find that the frequency noise spectrum is just the variation frequency squared multiplied by the phase noise spectrum, like so. And just to illustrate here, I've computed the same spectrum for the same random walk using both of the two approaches. And you can see that for the multiply by f squared approach, we actually avoid this little numerical artifact in the end here. And I'm not sure if that's always going to be the case, but it turned out to be the case for my simulations here. So just be aware of that, and it's always a useful mathematical fact to keep in mind. Now, of course, we can also compute the frequency noise spectrum for our random walk plus 30 GHz phase modulation in the phase domain, and we see that it's completely flat apart from this very strong spike happening here at 30 GHz. So here it's even more obvious that the laser's phase is being modulated at 30 GHz, like so. We can also plot in the frequency noise spectrum for that uncorrelated Gaussian process I showed earlier. And in this case, you'll see that actually scales up as f squared, because in the phase domain, this was completely flat. But then when we multiply by f squared to get the frequency spectrum, it of course scales as f squared. And the logic still applies that if you see something in here that scales as 1 over f squared, it means that the laser color, or the laser carrier frequency, is undergoing a random walk. So again, it's possible for not just the, let's say, the phase to undergo a random walk, but for the frequency itself to undergo a random walk, like so. And just for illustration purposes, I've also downloaded some spectra here for two different lasers that we can analyze. And again, note that this is the frequency noise spectrum measured in the absolute square value. So apart from the spectrum we saw earlier for the phase noise, this is actually in absolute square units. And we can note that both of these lasers exhibit 1 over f squared behavior here in the frequency domain, at least in the range from 10 Hz up to 1 kilohertz. And then for, I should mention that these horizontal lines here basically correspond to the uncorrelated frequency noise that we'd have for a laser with a given E-field line width. For example, if it has 1 megahertz of line width, then this is the level that we'd expect for the frequency noise that's uncorrelated to arrive at. We can see that they both arrive here at 100 kilohertz approximately. So probably if we were to measure on a fairly short time scale, we'd find that the E-field spectrum line width would be around 100 kilohertz here. And you can also notice that the green laser has some like weird spikes happening at 10 kilohertz and around 100 kilohertz here. I'm not really sure where they come from, but the point is that now we can at least have a sort of a mental mapping between the flat behavior here and the uncorrelated behavior of the frequency evolution, and the straight line 1 over f squared behavior here, and the random walk taking place on that time scale. So clearly both these effects are playing in at the same time. Okay, what else can we say here? So the point is that the frequency noise spectrum is very useful if the thing you care about is laser color stability. And you can probably imagine that if you're doing some kind of spectroscopy experiment where you want to, let's say, align the laser with a certain atomic transition line, then you're really interested in making sure that the laser is very stable and doesn't oscillate back and forth too much compared to the location of that transition. So in that case, knowing the frequency noise spectrum might be very essential. But of course, it also obscures some of the laser power information that the E-field spectrum provides us, as well as some of the timing behavior. So which one you end up presenting, of course, depends on your application. So I just want to make a quick summary of how to analyze these different spectra before we finish off the video. So if you have a random walk that takes place in the phase domain, it means that the phase noise spectrum will scale as 1 over f squared, and the frequency noise spectrum will just be constant, indicating that the frequency evolution is completely uncorrelated in time. If you have a random walk that takes place in the frequency domain, however, it means that the frequency noise spectrum is going to scale as 1 over f squared, and then because of this f squared conversion between the phase noise spectrum and the frequency noise spectrum, the phase noise spectrum is actually going to scale as 1 over f to the 4th power. Also, if the phase function is simply uncorrelated, it means that the phase spectrum will just be flat and therefore uncorrelated, and the frequency noise spectrum is going to scale as f squared with a positive up here, of course. And then finally, if there is uncorrelated behavior in the frequency domain, then you simply get constant behavior here in the frequency noise spectrum and 1 over f squared behavior in the phase domain. And of course, you probably already noticed that the first entry and the final one are basically identical. So whether you say there's a random walk in the phase domain or uncorrelated variation in the frequency domain, that's basically the same statement. Note also that in the particular case where this is random walk is taking place in the phase domain, you get an average electric field spectrum that is basically a Lorentzian. So I hope you found this video on phase and frequency noise interesting. Feel free to check out some of my other videos over here, and stay tuned for more. Bye bye.